The problem that we have is this. We're trying to evaluate some sprays. We have 3 sprays. We have spray number 1, spray number 2, and spray number 3. And these sprays, the effect that they have is they change the nitrogen content of the leaves on these trees. And each spray then is applied to 4 trees. So each one is tree 1, tree 2, tree 3, and tree 4. So 1, 2, 3, and 4. Tree 1, 2, 3, and 4. And then from each tree, we're going to sample a series of 6 leaves. So for each one here, it's 6. I'm not going to draw all of them in because it gets too busy. Okay, so as we indicated last time, the challenge that we face is this. The leaves are attached, physically attached to the tree. You cannot pick up a leaf and move it from one tree to another. So what you find in that leaf is a consequence of the tree that it's attached to. In addition to that, the trees are firmly rooted in the soil, so you cannot pick up a tree and simply move it over someplace else where you're going to apply the spray. Now, if you think about it, if you're going to apply this spray here and you're applying the spray to tree number 1, some of that spray is going to end up on the neighboring trees. So we have to set this up in a way where we're not going to get that kind of cross-contamination. So if we have 3 sprays here and we're applying spray 2, we need to make sure that none of spray 2 is landing on trees that should be receiving spray 1. So the design now is just a little bit more complex. Okay? Now the model that we're going to use looks just like, at least at first glance, it just looks like every other model we've ever put up, except now we're going to have 3 subscripts. So we have Y, I, J, K. So I for treatment, which is the spray. J is for our experimental units, which are the trees. And then K is for the subsamples, which are the leaves. So Yijk is going to be equal to mu, which is our overall mean, plus alpha I, which is our treatment effect for spray, plus there's going to be this variation that's associated with the experimental unit. So we're going to have to add beta. And this is where it gets just a little bit tricky. Because the betas, the trees, are firmly rooted in the ground. Okay, I can't just pick them up and move them. So if this tree happens to be on a south-facing slope and the next one is on a north-facing slope, I expect to see some variation amongst those trees, which has got nothing at all to do with the spray. All right? Fine. We can deal with that in all kinds of different ways, but that's further compounded by the fact now that I'm taking subsamples from those trees. So if you think about it, my tree, right, and my tree has these leaves, in some way I have, my tree is nested inside the spray. So I've got something going on. And the way I'm going to indicate that is I'm going to have I, comma, j. So normally I would put beta I, j like that. But what I'm doing now is I'm going to put parentheses around the I. And what I mean by that is that I have some nesting going on here. So the tree is nested within the spray. Okay? I can't pick up a tree and move it to a different spray. Then in addition to that, I'm going to have my error term, my epsilon, and typically I would write epsilon ijk, except now what I have is I have my individual leaves, and they are nested inside my spray tree combination. So the way I indicate that nesting is by putting parentheses around the subscripts. All right, so I've got my subsamples, I have my experimental units, and I have my treatments. Okay? So far, so good. If I didn't have this nesting, this would be a trivial exercise. It would be easy. It's no big deal. We've been to that rodeo before in some way. I mean, we did that when we did a Latin square design, right? Although in a Latin square design, we had all these constraints. We're free of some of those constraints now, but we have other constraints on us. So now what I've got is I've got I is equal to 1 all the way to A. I've got J is equal to 1 all the way to B. And I've got K is equal to 1 all the way to N. The sum of all of my alpha i's is going to be equal to 0. My betas, ij's, are going to be identically normally distributed with mean 0 and variance sigma b squared. My epsilons, I, j, n, k, are going to be identically normally distributed with mean 0 and variance sigma e squared. All right. Now, we're going to make the assumption that the variation in nitrogen from one tree to the next is going to be the same, okay, regardless of which spray we're using. It's a pretty strong assumption. Probably won't turn out to be true, but it's fine. We'll deal with that. The next thing is we're going to assume that the variation in nitrogen from one leaf to the next is going to be the same regardless of tree and leaf. That's what we're saying right here, okay? And then we're also going to assume that knowledge of beta gives us no knowledge of the epsilon. So knowledge of which tree we're on tells us nothing about what's going on with the leaves. So knowledge of what's happening with the experimental unit tells us nothing about what's happening with the leaves, which on some level you know is probably not accurate. Okay? All right. So how can we...
Do you mean like the trees without the sprays are...
Well, every tree gets a spray, right?
Yeah.
So we have, every spray had 4 trees in it, right?
Mm-hmm.
So knowing which tree it is tells you nothing about what's going on with the leaf. Except, of course, the tree is nested within the spray.
Okay, yeah.
All right? All right, so now comes the hard part. What we want to do now is figure out what our sums of squares are going to be. So we're going to do this the way we always do it. We're going to subtract mu from both sides. And then I'm going to replace mu with my best estimate of mu. So this is now going to be the total variation. So the total variation is going to be yijk minus, and my best estimate of mu is going to be y bar dot dot dot. So that's the average across all leaves, all trees, all sprays. And of course, we're going to, with those in parentheses, square it, add it up across all i's, j's, and k's. And that then gives us our total sum of squares. All right. Now, that's going to be equal to, we now have to estimate alpha. Well, that's going to be relatively straightforward. Okay? That's going to be yi dot dot bar minus y bar dot dot dot. And then, of course, we're going to add that up and square it. Okay? And I could go ahead and put my triple sums out there, right, and square that. I'm squaring both sides of the equation. So I'm going to do the same thing over here, but now I'm going to multiply this times bn. So that's from I equals 1 to a. And then, of course, I'm going to square it. Okay. Now, let's try and figure out, so there's my alpha right there. Now let's try and figure out what the beta is. So my beta is going to be from yi j dot bar minus y bar I dot dot. Quantity squared, a double sum times n. So I'm looking at my spray tree. I'm averaging across leaves, right, for my spray tree combination, and I'm subtracting off the mean for the spray. Okay? Plus, now I need to do my epsilon. So that's going to be the triple sum. I'm going to do yijk minus yij dot bar. Notice how this is different from that, and I'm going to square that. Plus all of the cross products. But we've made these assumptions about independence. So all cross products, if our assumptions are true, all those cross products equal 0. If the assumptions are not true, that's no longer the case. All right? So the assumptions are important. The reason the assumptions are there is so that we can get rid of the cross product terms. All right. If you go to the web page, you'll see that I have the data up there. I'm not going to write all those numbers down on the board. But let's write down what the Anova table looks like. So at first blush, it all looks pretty simplistic. Certainly easier, for example, than when we did the Latin square. But actually, it's not easier. So let's think about what this is. Here's the total variation. Here's the variation from the spray to the overall mean. Here's the variation of a spray tree combination compared to the spray. Here's the variation of the individual leaf from the spray tree mean. So let's look at that diagrammatically. So here we have our spray. We have spray number 1, 2, and 3. And within each of those we have 4 trees. Tree 1, 2, 3, 4. Tree 5, 6, 7, 8, 9, 10, 11, 12. And then within each of those we have our 6 leaves. Okay? So this one right here says we're looking at the average for spray 1 against the overall mean. So we're computing the average for all of that and comparing it to the mean. The next one, we're looking at the average for the spray tree combination. Now, spray tree combination, we're looking at that one, comparing that to that. Okay? Now the last one, we're comparing the individual leaf to the spray tree mean. So here is our spray tree mean, and we're comparing our individual leaf, that thing right there, to that. So now you can see this hierarchical, nested structure. I'm no longer going across like this. I'm going down like that. Okay? All right. Let's write out the Anova table. I left my book. Damn it. Sorry, I'll pull it up on the web, I think. All right, so our Anova table, we're going to have source, degrees of freedom, mean square, and expected mean square. When I read a paper and they say we did a nested analysis of variance, I always check to see if they've included the Anova table, and they never do. And I'll show you why in just a moment, okay? Or you'll see why when you look at the video for the R script for the nested Anova. So first of all, we have our treatment, which is our spray. Right, this is our treatment. And there we have, for degrees of freedom, we have A minus 1 degrees of freedom. I didn't put some squares in there, did I? Let's move this. Put sum of squares right there, and put degrees of freedom right there. I have A minus 1. Okay. Our sum of squares then is B times N times the sum of Y I dot dot bar minus Y bar dot 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 quantity squared. For within treatment, among samples, I have N times the double sum, so across A and across B, of Yij dot bar minus Yi dot dot bar quantity squared. And now I have A times B minus 1 degrees of freedom. Let's see, does that make sense? So I have A sprays and B trees. Okay? Within each spray, I have B trees. So B goes from 1 to 4 in this example. So what I'm trying to estimate for each of these is that beta parameter. Okay? So beta I paren J. So I lose 1 degree of freedom within each spray for trees. And I have 3 sprays, so I multiply that times A. Okay? All right. Now, the residual. here I have the sum across A, the sum across B, and the sum across N of y I j k minus y I j dot r quantity squared. And the degrees of freedom, well, let's see, what are we estimating? I'm estimating epsilon, but I'm estimating epsilon inside each tree. Okay? So I'm losing 1 degree of freedom there. I have n leaves within each tree, so n minus 1. And I have b trees times b, and I have a sprays, so it's ab times n minus 1. And then my total is going to be the triple sum of yi j k minus y bar dot 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 quantity squared, and degrees of freedom is going to be a times b times n minus 1. What's the parameter that I'm estimating? I'm estimating what? Mu. Okay? There's my, I've replaced mu with y bar dot dot dot. Let's see if that works. Does this plus this equal this? Let's see. Got a minus 1 plus a times b minus 1 plus ab times n minus 1. That gives me a minus 1 plus ab minus a plus abn minus ab. So plus ab minus ab. A minus a. So abn minus 1.
Yep.
Just what I have right there. So it's additive. So that plus that plus that will also equal that. All right, now my mean squares are going to be simply, and I'm going to, instead of writing all that down, I'm going to write SS TRT. So SS treatment divided by a minus 1. Here I've got SS treat within, I'm just going to put within, so the sum of squares within divided by a times b minus 1. Here I've got SSE for error divided by ab times n minus 1, and I don't have to worry about that one. All right. Now let's write down what the expected mean squares are. Okay? My expected mean square here is sigma e squared. Yay, team. It's always sigma e squared. The expected mean square here is sigma e squared plus n sigma b squared. And the expected mean square here is sigma e squared plus n sigma b squared plus bn sigma a squared. All right? Why? Because B is the trees, so the variation that I get here is the variation in the leaves plus the variation amongst the trees plus the variation resulting from sprays. Here, within my sprays, I've got my variation amongst the leaves plus the variation amongst the trees. And here I just have the variation amongst the leaves. So now the question is, what's the F-test? And this is where some kid who just learned how to plug in the numbers is going to fall on his face. Grad students have gone to their defenses and said, I did a nested analysis of variance, and this is what I did. They put the table up, and they've done the wrong F-test. There you are, you're not a member of the committee, but you're in the audience, and you go, when they open it up to questions, you go, excuse me, it's not pleasant, it's a mess. So what's the F-test? Well, what would you do if you were totally naive? Well, you take this one and divide it by that one.
Mm-hmm.
And that's what 99.9% of people do. And it's wrong. Why is it wrong? Because if you do that, then you get sigma E squared plus n sigma B squared plus B n sigma A squared divided by sigma E squared, which is equal to 1 plus n sigma B squared divided by sigma E squared plus Bn sigma A squared divided by sigma E squared. So now imagine that ends up being bigger than 1.
Okay,
Great.
I think I get it.
Why is it bigger than 1? Is it bigger than 1 because of, well, that's not good. Okay. Is it because of trees? Or is it because of spray? You don't know. You got nothing.
Mm-hmm.
But it's going to be big,
Yeah.
right? And the reason it's going to be big because that thing is small. Here you've added the variance associated with the trees, and you've added the variance that's associated with the spray. Okay? So of course it's going to be big. And plus, the degrees of freedom is bigger. Okay? Which is going to make that thing, which is going to make epsilon smaller. So sure. And of course, when people write their papers or their theses or whatever, and they say we did a nested analysis of variance, and they say that they give you the p-value, but they don't give you the f, and they don't give you the degrees of freedom associated with the f. So when you've read the paper, you write the author or you email the author and say, what were the degrees of freedom associated with the f? And they'll either say, well, I don't remember, or I don't know, I'll get back to you. Or they'll send it to you and you look at it and go, yeah, well, that's wrong. Okay? Because that's the test that they did. So where is the appropriate F test?
They're not, so if they just do that, they're not doing the nested part, are they?
They're just, yeah, they're
Yeah.
completely blowing off the fact that this is a nested design.
Mm-hmm.
Which leads you to ask the question, why the hell then did they even bother to call it a nested design? What do they think is going on? They think there's some kind of magic going on. So what's the appropriate F? That's the $64,000 question. It's in my contract, I get to drink coffee. It's the only reason I took this line of work. Because they let you drink coffee. When I worked in the steel mills, they'd never let you drink coffee. Same thing when I used to be a machinist later on. They wouldn't let you drink coffee either. Of course, you didn't want to drink it either because there was all this oil floating around in the air, landing on everything. And it's nasty. So where's the F test?
Would you have to write it? No. thought I,
Well, there is an F-test there.
yeah.
Well, if that ain't it, the only other thing that's up there is this one.
That's
So-
what I was looking at.
What do you get then? Then you get sigma E squared plus n sigma B squared plus B n sigma A squared divided by sigma E squared plus n sigma B squared. So now you divide that, and that equals now 1 plus Bn sigma A squared divided by sigma E squared plus n sigma B squared. So here you're accounting for variation amongst the leaves and variation amongst the trees. Okay? Now you have an F-test.
Okay.
That's the F-test that you want. It's that divided by that, not that divided by that. And you have fewer degrees of freedom.
Okay.
That's why people don't want to do that, right? It's harder to find significance here than it is comparing that to that. Comparing that to that, yeah, it's going to be a big number. Comparing that to that, it's going to be a smaller number. It's less likely that you'll find the difference. But it is the correct answer. So the hard part is recognizing when your design, well, two things are hard. One is recognizing when your design is nested. Unfortunately, as biologists and or as ag people, we oftentimes have nested designs. You're working in one river, comparing it with what's going on in another river, what's going on with another river. It's nested. Okay? That's an issue. But that's not the worst of it. The worst of it is this. Let's imagine you've gone through all this work and just by chance you lose one leaf. Okay? You've lost one of your subsamples, just one. So instead of having 6 leaves for each tree, you've got 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 6, 5. All you did was lose one leaf. What do you do?
Lose one from the other samples, or from each treatment.
Yeah, of course, there was a reason why you went with 6. Okay? The reason you went with 6 was because you did your homework and figured out that the minimum number you needed to be able to find a significant difference, if one existed, was 6. Okay? So you did the preliminary study, you figured out what epsilon E was, right? And you said, okay, as long as I have this many degrees of freedom, my epsilon E is going to be this size, which then means, right, I'm going to end up with a good chance of finding a difference if one exists. But you may not have an option. Okay, you may have to throw one out. Let's look at where the F-test is if we lose one. You're going to need more board space. Sorry. Got to erase all of this. And all we're going to do now is write down the expected mean squares. Oh, I do have the, before I do that, let me give you, oh no. Oh, sweet, I've got it, yes. Let me give you what the actual, these are the numbers that you should get when you do your analysis on R for these data, okay? So here's source, and then I'll show you what happens. Sum of squares, degrees of freedom, mean square, and then tabled F and computed F. All right? So spray, spray is 633.402. It turns out that the numbers you get in R are just a little bit different. Why? Because when I did this, I did it by hand with the handheld calculator, and there's random rounding error on the handheld calculator, okay? I have 2 degrees of freedom there, and my mean square, 633.402 divided by 2, gives me 316.701. For within spray, among trees, I get 246.903. I think that's a 9, yep. And I get 9 degrees of freedom right there. And 246.903 divided by 9 gives me 27.434. For the error, I get 129.143, and I have 60 degrees of freedom. Yay, that's awesome. And here my mean square is 2.152, and then my total is 1,009,1009.406. Better 9 there. 1009.406. I have 71 total degrees of freedom. And now, what's the F? Well, we know that the F is this divided by that. The naive person goes, oh yeah, this divided by that. Well, that divided by that gives you an F that's about really big, okay? About 150 or something like that. This divided by that is about 10 or 11, okay? But the correct F is this divided by that, not this divided by that. So my correct F is going to be 11.54. My tabled F is 4.26. This is bigger than that, therefore this is significant. Okay? This divided by that gives me 12.75, and my table value is 2.04. But importantly, it's that divided by that to give you that. That's what you cared about. So why even bother to give this? Well, what is this? This is significant, right? So what does that tell me? So this is sprays. This is among trees within sprays.
Okay.
So amongst trees, I know that I have a significant tree effect within the sprays. Well, Christ, that's why I did the nesting in the first place, because I suspected that might be the case. Or I suspected the aquarium might be influencing, or the river system might be influencing it. Okay? If this were not significant, if this was not larger than the table value, then I could justify pooling this with this. I could combine those two things together, which then I have 69 degrees of freedom instead of just 9. And if this wasn't significant, I could now divide that by the pooled value there, and then potentially find a significant difference. But in order to do that, this term right here has to be not significant. If it's not significant, I can pool it. If it is significant, forget about it. Okay? All right, so let's look at what the actual expected mean squares are going to be if we lose one leaf. So when you run your analysis, when you run your analysis, make sure that you get within, a couple of hundredths. Make sure you come up with the same numbers that I put up on the board. If you don't have those numbers, you did something wrong. Okay? All right, so let's define a few variables first, okay? A is going to be number of treatments. N, I sub j, is going to be the size of the subsample from the jth member of the sample on the ith tree. All I'm doing is I'm saying that I'm going to have different samples for different trees. Okay? I'm not going to have the same number of leaves for each tree. That's why I'm subscripting Nij. B sub I is going to be the size of the sample from the ith treatment, because now in one spray, instead of having 24 leaves, I've only got 23. So Vi is going to be 24, B2 is going to be 24, B3 is going to be 23. So I have to subscript the B's. Ni is going to be the sum of the Nij's from I equals 1 to B sub I. Okay? And then N is going to be the sum from I equals 1 to A of all the Ni's. That's the total number of observations. Okay. Let's do the easy one first. So let's write down the expected mean square for total. Okay? I don't even have to do that. Yeah, I do. I'm going to give you source, degrees of freedom, sum of squares, degrees of freedom, and expected mean square. So total sum of squares is going to be the triple sum of Yij k minus y bar dot 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 quantity squared. And the total degrees of freedom is going to be equal to n minus 1. For the residuals, so for error, I'm going to have triple sum across A, B sub I, N, I, J of Y, I, J, K minus Y, I, J dot bar quantity squared. Degrees of freedom is going to be n minus the sum from I equals 1 to A of B sub I. My expected mean squares is going to be that divided by that, which gives me sigma E squared. Within treatment, among samples, I'm going to get the sum across A, the sum across B sub I of Nij times Yij dot bar minus Yi dot dot bar quantity squared. The degrees of freedom is going to be the sum of B sub I minus A from I equals 1 to A. And the expected mean square is going to be sigma E squared plus n minus sigma cross A, I equals 1, of sigma from I equals 1 to A of Nij divided by Ni, all of that divided by the sum from I equals 1 to A of B sub I minus 1, all of that times sigma B squared. Okay. Here, for spray, or for treatment, right, I'm going to have a double sum across A and B sub I of Nij times yi dot dot bar minus y dot 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 bar quantity squared. Degrees of freedom is A minus 1. My expected mean square is going to be sigma E squared plus the sum of across A, I equals 1, the sum from I equals 1 across A of Nij squared divided by N sub I. Oops, that's squared as well. Minus, whoops, like that, minus the double sum across A and B sub I of Nij squared divided by N, all of that divided by A minus 1, and all of that times sigma B squared plus the sum Ni squared alpha I squared divided by A minus 1. When you get your master's degree in statistics, you take 2 exams as part of that master's degree. They are the 2 actuarial exams. And if you pass both actuarial exams, you only have to pass one of them to get the degree, at least at New Mexico back in the early 80s. If you pass both of them, then you can become an actuarial scientist for some big insurance company, and those actuarial scientists make a lot of money. You know, so coming fresh out of school, you know, with a master's in statistics, having passed both actuarial exams, you can expect to pull down 200 grand easy. Okay. One of the things that you have to do on the actuarial exams is derive these things using the rules of expectation. And it looks daunting, it looks hard, but if you understand the rules of expectation, it's not. It's pretty straightforward. Okay? But the reason I'm putting it up there is maybe it looks different back here, but you look at that and say, okay, what am I going to divide by what? Because if I divide this by that, all I get rid of is that.
Yeah.
And I have this whole mess up here. All right? If I divide this by this,
Yeah.
I get something totally weird because this part doesn't look anything at all like this part right here. They're different. So that's the next bugaboo. When you do R, it doesn't care what your sample size is. It's going to spit out the numbers no matter what. And you think, because it gave you numbers, everything is neat and groovy. And it's not. Because you divided this by this, and you come up with some number, and the number you came up with is horseshit. You go ahead and write the paper and submit it, and the editors don't know what's going on. They don't understand it, so they say, yeah, that's good. until 10 years down the road, some punk-ass kid just out of college is going to discover your error and call you out on it, and then you're going to look like an idiot. Okay? Lose one leaf, forget about it. Now, what do you do if you lose one leaf? You give up? Go home?
No.
No way. You're into this thing. Now what you have to do is figure out some alternative way of analyzing these data. Back in the 50s, what they would have done is this. They would have looked at your setup, spray 1, 2, 3, trees 1, 2, 3, 4, leaf 1, 2, 3, 4, 5, 6. And they would have looked at that and they would have said, all right, we've lost one leaf. We lost that one right there. Let's figure out what it would have been. Let's guess at what it would have been by taking the average here and comparing it to the averages across there and the averages across there. So let's use sort of this double layered averaging technique to figure out what the value should have been right there.
What if the spray 3 produced completely different results from spray 1?
Yeah, so that's why you have to compare the
Yeah.
average from this spray to that spray to that spray and make the adjustment.
Okay.
And then you have to look at the averages across the trees and make the adjustment. And then you say, okay, based on the adjustment that I made across sprays and the adjustment they made across trees, I'm going to assume that that is going to be the average of what those leaves were and just plug in that value. That's what they would have done in the 50s. Until by the time the 70s came around, people are going, whoa, wait, I think that's called cheating. And it is,
Yeah.
okay? So you don't do that anymore. Now, you have to rely on a different technology to solve that problem. And that's what we'll do in the second half of the semester, figure out a different technology to deal with that particular problem. Okay, so that's nested analysis of variance. Don't lose samples if you're doing a nested design. Don't. What that means is, when you hire people to collect your samples, pay them well. You know from the brick data from way back when, people that make more, work more, pay more, okay? Vote union, yay. Oh wait, that's socialism. Okay. Let's do one more design. Actually, what we're going to do now is like a gazillion new designs. What we're going to do now is something called so let's see, what have we done? We've done confidence intervals, that's sort of our first test. We've done t-tests, a whole bunch of different kinds. Right? We've done a completely randomized design. We've done a randomized complete block design. We've done a Latin square. And now we've done a nested. All of these are considered one-way analysis of variance design. Well, all of these are considered one-way ANOVAs. Although a Latin square, you can set it up as what's called a Greco-Latin square. So just instead of being a square where you have hospital, method, and detergent, you could have another dimension as well, so you could look at two factors at once, right? And randomized complete block, you can also do randomized incomplete block and all kinds of weird permutations of that, okay? So there are we've just scratched the surface here. There are lots and lots and lots of different sorts of designs here. you can take an entire semester-long course in just block designs. What we're going to do now is we're going to make a giant leap and we're going to start talking about multi-level ANOVAs. So instead of just doing a one-way ANOVA, we're now going to start talking about n-way ANOVAs. And the common phrase that we use for n-way ANOVAs, two-way ANOVA, three-way ANOVA, four-way ANOVA, we call them either factorial designs or cross-classification. So cross-classification designs. Okay, so what we want to do now is we want to study two or more treatments at the same time, right? So for example, we might be looking at fertilizer concentration and seed type. So we might have different types of seeds, so seed types. And we decide, well, some varieties of seeds might be better than other varieties of seeds. Maybe we can buy some seeds from Monsanto and different seeds from some other company or something, and we could test those seeds to see which one is better. We might have available to us 2 or 3 different kinds of seeds. But then we also might be thinking about how much fertilizer, so we might have different fertilizer levels. And we recognize that it's possible that the different seed varieties might respond differently to fertilizer levels. So a higher concentration of fertilizer might affect one seed variety differently than a different seed variety. Okay? One seed variety might respond to the higher fertilizer level by growing better. The other one might respond by growing less. So that's where we are now. And the way we're going to set the model up is like this. So the data that I will give you, not today, is that we have fertilizer levels. And in the data that you will get, you have low, medium, and high. And it's important to remember that these are factors. So I'm not saying 5 pounds per acre, 10 pounds per acre, 15 pounds per acre. That's not what I mean. And if my low is 5 pounds per acre, I mean 5 pounds per acre, not 5.1 pounds per acre, or 5.5 pounds per acre, or 4.9. I mean exactly 5. Okay? In other words, if here's fertilizer level, and I say this is low, this is medium, and this is high, right? And I say there's low, I say I have that much. What I'm saying is all my variation now is going to be in that direction. I'm not going to get any variation in that direction. Okay? So when I say I have a low concentration, I mean a low I'm going to ignore all that noise going off in that direction. In practice, it may very well be that you have 4.9 in one plot and 5.1 in the next plot, but you're ignoring that. If you don't ignore it, then it changes from being an analysis of variance problem to being a regression problem. Okay? And that's different. A lot of similarities, but it is different. So we have no variation with respect to these levels. The next variable that I have is seed type. So in this example, I might have 2 seed types, seed type A and seed type B. So now I have lots of observations there and lots of observations there. Lots there, lots there. And importantly, I have a balanced design. In other words, I have the same number of observations here, as here, as here, as here, as here, and here. In the nested design, it's absolutely crucial. Here, there are ways to get around it if I don't have a balanced design, but it makes life more difficult. Okay? Here at least, if we lose an observation, we can figure out what the appropriate f-test is and still do it. In a nested design, we can't. Okay, so let's write down the model. And now, it should be painfully obvious. When we say, let's write down the model, we're going to do y, I, j, k is equal to u plus alpha I. Alpha I will be fertilizer level, okay? Plus beta j, which will be seed type, plus alpha beta in parentheses ij plus epsilon ijk. In other words, what I mean by this term right there, I mean there's a possibility that I have interaction. In other words, one seed might respond differently to higher fertilizer levels than the other seed. Oh, we talked about interaction before, didn't we? We used an example when we were talking about Latin squares or about block designs. Remember that diagram that we put up? Where for the two different treatments, if the lines were like that, we said they were additive and there was no interaction. And if the lines crossed, we said that there was interaction. In the previous design, we said we're assuming there is no interaction. We're not making that assumption anymore. Now we're saying, fine, interaction, great, whatever, we don't care. All right. We need to make some assumptions, okay? Our assumptions are going to be that the sum of all the alphas is equal to the sum of all the betas, beta j's, is equal to the sum of all the alpha, beta, ij's. That's the sum across I is equal to the sum across j of all the alpha, betas is equal to 0. And I'm also going to assume that epsilon I, j, k is identically normally distributed with mean 0 and variance sigma e squared. In other words, I'm going to assume homoskedasticity as opposed to heteroskedasticity. Remember those terms? All right. Let's see. Let's figure out what our estimates of all of these different terms are. Let's see if we can do that. Well, just like we've done with every model up to this point, we're going to take mu and subtract it from both sides and replace it with our best estimate of mu. So we're going to have y, I, j, k minus mu, our best estimate of mu is y bar dot dot dot. Added up across all ij's and k's and squared, just like we've done every other time. What's our best estimate of alpha? Our best estimate of alpha is going to be yijk minus y bar dot dot dot. And then sum it up across all ij's and k's and squared, right? What's our best estimate of beta? That's going to be whoops, I screwed up. It's not yijk, it's yi dot dot bar. Because otherwise it would be exactly this, wouldn't it?
Yeah.
Yeah. So now it's going to be y dot j dot bar minus y bar dot dot dot. Okay. What's epsilon going to be? There's alpha. There's beta. Now I need the alpha beta term, and I need the error term. Let's do the error term first. So my error term is going to be yijk minus yij dot bar. Let's see, does that make sense? Let's remember what the structure of our data set was. We had fertilizer levels 1, 2, and 3, and seed types 1 and 2, or A and B. So what are we doing? For alpha, we're comparing fertilizer levels. So we're looking at that variation. For betas, we're looking at that variation.
Okay.
For epsilon, we're looking at the variation
Diagonal.
in, well, no, the variation in here. Okay? So for each, it's yijk minus the mean
yeah, we're on it.
for that fertilizer seed combination.
Yeah.
So we're looking at the variation within each of these experimental units. So now what we have left over is this alpha beta part. Let's figure out what it has to be. So let's just call that x. So we have yijk minus y bar. I better do this neatly. All right, we're good to go. Hey. Okay, so let's do this solution now. So I have yijk minus y bar dot dot dot. And I'm going to subtract from that each term over here except for x. So from that, I'm going to subtract yi dot dot bar minus y bar dot 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 minus y dot j dot bar minus y bar dot 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 minus yijk minus yij dot bar equals x. Okay, so I have yijk minus y bar dot 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 minus yi dot dot bar plus y bar dot 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 minus a minus, right? Minus y dot j dot bar plus y bar dot 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 minus yijk plus yij dot bar is equal to x. All right, so a couple of things cancel out. Minus y bar dot 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 plus y bar dot dot dot. So those two cancel out. All right. Minus, there's yijk minus yijk. So those two cancel out. So now I've got yij dot bar. So that's my average for this value in there, minus yi dot dot bar minus y dot j dot bar, yi dot dot bar minus y dot plus yij dot bar. Oh, I've got two of those, don't I? Yij, did I make a mistake? Yij minus yij plus yij. Nope, that's different. How did I get two yij's? Where's my other yij? Oh, you guys led me astray. You let me screw up. Start over. I work good on my knees. I spent most of my life down on my knees. It's only fair. All right. Yijk minus y bar dot 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 minus yi dot dot bar. Yi dot dot bar plus y bar dot 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 minus y dot j dot bar plus y bar dot dot dot. Let me know if I'm screwing up. Minus yijk plus yij dot bar is equal to x. All right, plus y bar dot 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 minus y bar dot dot dot. Yijk minus yijk. All right, so now I've got yij dot bar minus yi dot dot bar minus y dot j dot bar oh, I've already done this one. Right? I moved that one over there.
Mhm.
So now plus
So, y.
y bar dot dot dot. Yay, team. I thought I had screwed up. Well, I no doubt that it's not an uncommon occurrence, but all right. Hey, does that make sense? Let's see. What is yij dot bar? That's the average inside the ijth sampling unit. And I'm looking at the deviation from that to the average going in that direction. And then I'm looking at that, the deviation of that from
Yeah.
in that direction. And now I'm supposed to just subtract one mean, right? That's what a standard deviation or a variance term is, right? Observed minus expected. I've subtracted off two expecteds, so now I have to add one back in. My best guess
Okay.
is the overall mean. We did that before.
Yeah.
So that makes perfect sense. So there is my interaction term. So my interaction term is yij dot bar minus yi dot bar minus y dot j dot bar plus y bar dot like that. Notice what we've done, okay? If I was not looking at the interaction term, what would I have? If I wasn't looking at the interaction term, where would all of this noise be? It would be in there. So by pulling out the interaction term, I've made epsilon smaller. Why do I care? Because when I compute the Anova table, I want the epsilon term to be as small as possible because I'm looking at the relationship of alpha to epsilon.
Yeah.
The smaller epsilon is, the bigger that ratio is. Or I'm looking at the ratio of beta to epsilon. The smaller epsilon is, that ratio will be bigger. So what I've done here is I've partitioned that noise out of the error term. That's the magic of analysis of variance. Partitioning the variance. We want to take that noise out of the error term, make the error term as small as we possibly can. When you're designing your experiment for your masters, what you want to think about is where is the variation? How can I partition it out to make my error term as small as I possibly can? All right, let me give you, without going through all the gory computational details, let's put up the Anova table, and then let's see, do I have this one solved? No, that's all right. I'll ask you to solve it. Okay? So let's put up the Anova table. So we have source. And I have sum of squares, degrees of freedom, mean square, expected mean square, and then f. All right, so source is do A. So do treatment A, which was fertilizer level. Do B, so variation due to B, which is C type. And then do AB. Then we have error or residual, and then total. So the sum of squares, SSA, is equal to B times N times the sum yi dot dot bar minus y dot 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 bar quantity squared. Here, sum of squares B is equal to A times N times the sum y dot j dot bar minus y bar dot 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 quantity squared. The interaction term SSAB is equal to N times the double sum of YIJ dot bar minus YI dot dot bar minus Y dot J dot bar plus Y bar dot 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 quantity squared. And then SSE is equal to the triple sum of yijk minus yij dot bar quantity squared. Degrees of freedom, move that column over just a little bit. Here I'm going to have a minus 1. Here I'm going to have b minus 1. Here I'm going to have a minus 1 times b minus 1. And here I'm going to have ab times n minus 1. And here I have ab times abn minus 1. At home, you can convince yourself that this plus that is equal to that. Okay? All right. Mean square is just going to be sum of squares a over a minus 1. This is sum of squares b divided by b minus 1. This is sum of squares ab divided by a minus 1 times b minus 1. This is SSE divided by AB n minus 1. And now the dreaded expected mean squares column. This one down here is sigma E squared. This one up here is sigma E squared plus B n sigma A squared. This is sigma E squared plus A n sigma B squared. This is sigma E squared plus n sigma AB squared. So what's the F test? What's the F test for fertilizer? Fertilizer is A. What divided by what? Well, what do you want to isolate? You want to isolate the variance associated with A. Where do I see some A's? Oh, I see an A right there. So I want to isolate that term. There's the epsilon.
Yep.
So it's going to be sigma E squared plus B n sigma A squared divided by sigma E squared. So that equals 1. Right, so that gives me 1 plus B n sigma A squared divided by sigma E squared. So that's the same as mean square for A divided by mean squared error.
Okay.
Equals mean square AB equals mean square B equals mean square A.
Okay. Yeah.
So C type, easy, that's mean squared for B divided by MSE.
Okay.
This one, easy, mean
MSE.
square AB
Yeah.
divided by MSE.
Okay.
All right. So, you do the analysis. You run your data, and what you really cared about was, is there a difference between the fertilizer levels? And it turns out you don't find a significant difference. The p-value turns out to be 0.06. You go, damn.
Oh, okay. I think you would input AB back into your error.
Well, if the interaction term is not significant,
Yeah.
you can say, oh, because this isn't significant, if this is not significant, it means that that
Yeah.
and that are really estimating the same thing.
Mm-hmm.
So you can now pool the interaction term in with the error term And by doing that, your degrees of freedom are now AB times n minus 1 plus the quantity A minus 1 times B minus 1. Now you have more degrees of
Okay.
freedom with the error, which is going to make your F-test much easier.
Yeah.
So if the interaction term is not significant, pool it. Okay? So in this cross-classification design, you can test 2 factors. Let's do 3 factors. We're not going to write down the whole table. Relax. They don't give us enough blackboard, whiteboard, whatever you call these things. Well, they start off being white. By the end of the semester, they're black. Let's look at 3 factors. Now we're going to have y, I, j, k, l equal to mu plus alpha I plus beta j plus gamma k plus alpha beta ij plus alpha gamma ik plus beta gamma jk plus alpha beta gamma ijk plus epsilon ijkl. So now we've got the 2-way interactions plus the 3-way interactions. Let's look at a 4-way ANOVA. Y, I, j, k, l, m is equal to mu plus alpha I plus beta j plus gamma k plus omega k l of beta gamma plus alpha beta plus I'm going to forget about all the subscripts for the moment, plus alpha gamma, I guess that should be theta, shouldn't it? Plus alpha theta plus beta gamma plus beta theta plus gamma theta plus alpha beta gamma plus alpha beta theta plus beta gamma theta. Am I missing something? Alpha beta 1, 2, 3 1, 2, 3 2. I think I have them all. Plus alpha beta gamma beta plus epsilon. You see a pattern? So as the number of factors increases, the number of parameters that you have to estimate increases very quickly. Okay?
Because whenever we combine A
Because-
and B in the last one, we're also combining B
All
and
the
C
interaction
and-
terms.
and
So now
D
you've got
Yeah,
2-way interaction terms plus 3-way interaction terms plus 4-way
Yeah.
interaction terms. You add another one. So all the 2 ways, all the 3 ways, all the 4 ways, all the 5-way interactions. So what do? What's the strategy? The first thing you do as a biologist, you ask yourself, okay, because here's the problem. The number of degrees of freedom you're going to need is enormous. So the first thing you can do is say, okay, some of these possible interaction terms make no biological sense. Don't care. It's not going to matter. So right from the get-go, you can say, I don't care about that interaction. I don't care about that interaction term. It doesn't make any biological sense. I don't care about that one. I don't care about that one or that one. And I don't care about that one. Now you don't even have to estimate them. Now what you can do is you can take all those degrees of freedom and all those things right there, they end up getting pooled in the error term. Okay? That's one solution to the problem. But you see how quickly it gets out of hand. I've seen ANOVA designs where there have been like 15 factors that are all being analyzed at the same time. And it's huge. Those are the sorts of studies that come out of the Centers for Disease Control. Do you see a potential problem, though, when you have a design that big? Yeah, the potential problem is keeping it all balanced. Because if it's not balanced, some of these estimations are going to be challenging. There are ways to deal with it, but it makes it more difficult. There is another approach, and that alternative approach is something that we'll start talking about next week. All right, that's it for today. Oh, so I will assign sometime over the next few days, probably end of the week, probably weekend or something, at least before we meet again next time, I will put up a data set for the two-way ANOVA, okay? And I will give you the R script so that you can run the data. I will give you what the results should look like, and then you should make sure that your results match. When you do the ANOVA for the nested design, pay very careful attention to the script that I'm using. In the R package, when you write the model, right, for the analysis of variance, pay careful attention how I'm writing the model, right? And now I've forgotten what the terms are. It's AOV, right? And then what was the response? Nitrogen as a function of, and then what did we have? Spray. And then I have plus error. And then I specify spray. And I've forgotten how I indicated the nesting. There are a number of ways you can indicate nesting. You can use a colon, or you can use a vertical bar, and then tree. So trees are nested within spray. By doing it in this way, I'm telling R that this is what you're going to use as the error term. And as long as you do that, in spite of the warning that it gives you, in spite of the error message that it gives you, this gives you the correct result. What is the error warning? The error warning is, it says, possible singularity. And what that means is, it's possible in the data set that there's a singular value. In other words, something that cannot be estimated. That's incorrect. Okay? I'm not saying R is wrong. R hasn't gone to the trouble to make sure, but it's just giving you a sort of primitive kind of warning. In some cases, the warning is applicable. In this case, it's not. So you can ignore that warning. Okay? Doing it this way will give you the correct Anova table. You're going to have to use another command, summary, and then all of this. And then close print. And then it'll give you summary. Okay? And then it'll give you the correct Anova table, or everything you need to complete the Anova table. So make sure you do that step. If you don't do that step, if you just do nitrogen against spray, it gives you the wrong answer. Or if you do nitrogen against spray colon tree, it gives you the wrong answer, because then it assumes that your error term is going to be the SSE, and that's not the correct error term. That's the step that most people miss. Okay, that's all for today. When we come back next time, we'll make sure we have the ANOVA finished up, and we'll start talking about other kinds of linear models.